All right, here we are back for the third, and this may actually be the final segment for sections 5.3 and 5.4. They really aren't that long, other than maybe a few. We may actually have a fourth segment to practice some of the skills. But my intention here is to develop the sum and difference formula for tangent, and then run as many of these applications as I feel are necessary. We've already done them for angles of 15 and 75 degrees in one form or another for sine and cosine, but we want to be able to develop a formula that involves tangent. Not that we couldn't find it, but we may not want to use two formulas every single time we do that. So this is considered to have some value to us. So let me ship over here. All right, hopefully everything's in focus. So this is, again, this is section, we've really moved into section 5.4, but since I haven't really been distinguishing that separation, I'm going to keep with that strategy. So I think this is awfully fuzzy. Okay, so first, let's start with this observation. If we wanted to make a tangent version of the formulas we've had before, we're saying, let's find the tangent of a sum or a difference. I'm going to work with this kind of both at the same time. I think it's appropriate at this point. So note that happens just by the quotient, one of the quotient identities. We know that that's equal to sine of the same argument, right? Whatever it happens to be, over cosine of the same argument. All right, and this is going to be the key because we have formulas for sine and cosine. Now we just need to sort of do a little bit of manipulation and clean this up. So recall from last time that the sine of a sum or difference is sine of the first thing times cosine of the second thing. And the SIGN is preserved, so that's plus or minus sine of the second thing times the cosine of the first thing. Okay, this is really bothering me. I think maybe the document camera is a little too close, and so it's having trouble focusing properly. I think that looks a little bit better. Okay, so this is the numerator. This is sine of A plus B. A plus or minus B. And then in the denominator, we have cosine of the first angle times cosine of the second angle. And remember that the SIGN is reversed here, so minus plus sine of the first angle times the sine of the second angle, okay? Now, what I'm gonna do, and this is gonna look a little bit weird, but basically, I'm going to divide every term by this term, this cosine A times cosine B term. Right? This seems sort of weird. Like normally when we have a complex fraction, we try to factor out the least common denominator, and then we eliminate it through a cancellation or whatever else. We're actually going to make this formula more complicated. And then it starts to simplify. So that's sort of the strategy. So understand what I'm doing is I'm basically multiplying by this term, which is 1 over cosine of A times cosine of B over 1 over cosine of A cosine of B. Notice this is just a fancy version of 1. Right? We have something over itself, it's always going to be equal to 1. So I'm multiplying this crazy looking expression by that to make it even crazier. And what we end up with is a pretty gnarly looking complex fraction that has sine of A, sine of B, or sorry, cosine of B over cosine of A times cosine of B. Right, so that's this first. That's this term. then plus or minus sine of B times cosine of A over cosine of A cosine of B. Right, that's this this term. This is all going to be over cosine of A times cosine of B over cosine of A times cosine of B. That's this term here. Minus plus sine of A times sine of B divided by cosine of A times cosine of B. Sorry about that. So let's look at this awful expression here for a moment. And what I want you to note is that you start to see a lot of things canceling, right? You've got, let's start with this first term. Notice that cosine cancels with cosine. And over here in this second term, cosine A cancels with cosine A. Down in the bottom, both cosine terms cancel. And then over here, look at what's left. In this first term, I have sine of A over cosine of A. Well, that's tangent of A, right? And on the second term, I have sine of B over cosine of B. That's tangent of B. Down here, this will entirely reduce to 1. And here I have sine of A over cosine of A. That's tangent of A. Sine of B over cosine of B. That's tangent of B. So I've got a product, and I've got a sum or difference up top and a product down in the denominator. So that's the simplification of this. It's kind of ugly to have to kind of complexify it so that you can bring it down to something a little more reasonable. But here's the net result. This is tangent of A plus or minus tangent of B, all divided by 1 minus the product tangent of A times tangent of B. Okay? So there's your formulation for tangent of a sum or difference. It looks a little awful, but it's the best we can do. And notice that I don't need to know anything about values of sine or cosine. All I need to know now is just values of tangent for known, exact values. So here what I'm gonna do is I'm gonna use this to derive a value. We're now on page 7, and I feel like this pen is kind of running out of ink a little bit. Let me shift to another one. So let's try this example. Let's take let's find what the tangent of 13 pi over 12 is. So remember, tangent 13 pi over 12. That's equivalent to 195 degrees. So this is an angle in quadrant 3 with a reference angle of 15 degrees. This is the kind of stuff you see. Now, what I suggested is when you see this 12th, this is clearly you should be using a sum or difference identity. I could either write this as something I know minus something that gets me back to 13 over 12, but it probably makes sense to use a sum. And anytime I'm just telling you, anytime you have a 12th where you're trying to write this, the first step is to pull out 45 degrees or pi over 4. So I'm going to write this as tangent of 3 pi over 12. That's my pi over 4, plus how many ever 12ths I need to get to the number I'm interested in, right? So 3 plus 10 is 13 pi over 12. Now I'm going to simplify these fractions so they start to look like things I'm familiar with. So this is pi over 4 plus, this is 5 pi over 6. Or equivalently, that's 150 degrees. Okay, so now that I've got them sort of broken up, I can apply my difference, my sum formula for tangent. So this is going to be tangent of the first angle plus tangent of the second angle over 1 minus the product tangent of the first angle times tangent of the second angle. Now, just kind of as an aside, remember that tangent of pi over 4 is actually equal to 1. That's kind of nice. But what about tangent of 5 pi over 6? Tangent of 5 pi over 6 is going to be a little bit ugly because this is, the reference angle is 30, and as you recall, tangent of the reference 30 degrees. Recall that the tangent of a 30-degree angle is square root of 3 over 3. This is a quadrant 2 angle, and so it'll have a negative sign. We've got minus square root of 3 over 3. Okay, so I'm going to substitute these values into this formula, and I've got 1 minus square root of 3 over 3 over 1 minus 1 times negative square root of 3 over 3. Which happens to be equivalent to 1 minus square root of 3 over 3 over 1 plus square root of 3 over 3. How ugly is that? So we're obliged to simplify this, not just because of the fact that it's a complex fraction, but also because it will have a radical in the denominator. And this, and since that's kind of a sketchy process that we haven't done in a while, I'm going to start with a fresh sheet of paper to address that issue by itself. Because this, when you're dealing with these tangents, sum and differences, you almost always have a very ugly looking formula that you have to apply all the rules of simplification to. So here's our sort of task. We want to simplify this expression. 1 minus square root of 3 over 3 all over 1 plus square root of 3 over 3. Okay, so let's tackle this in steps. This is a complex fraction. For complex fractions using what's the so-called method 2, we're going to multiply every term by the least common denominator of any internal fractions. Now notice this one's denominator is 1. This one's also 1. But we have 3 and 3, so the least common denominator of all terms is 3. So everything is going to get multiplied by 3. Now, when I distribute this, I end up with 3 minus square root of 3 over 3 plus square root of 3. So we've gotten rid of the complex fraction part, but now we have a radical in the denominator. And it's not even a simple one. It's a binomial. So recall, I've seen people try to do all kinds of weird things with this, but when you end up with the binomial, in order to get this out of the denominator, you have to multiply by the radical conjugate. Okay, so we're going to take whatever's in the denominator, and we're going to change the sign on the second term and multiply everything through by that. So we end up multiplying by basically the term that's in the numerator here. So we have 3 minus, that's just a coincidence though. 3 minus square root of 3 over 3 minus square root of 3. We haven't done anything crazy because that's that's not 0 over 0 or something. So now this is going to get kind of ugly. We got to FOIL these things out. Right? For whatever reason, when people start doing this, they try to take shortcuts which don't work or whatever else. This is just brute force. It's gonna take some manipulation to get to the right answer. So let's start with the numerator. Let's FOIL this out. First is going to be 3 times 3. Outside, 3 times negative square root of 3, so minus 3 square root of 3. Inside, we're going to get another 3, negative 3 times square root of 3, so negative 3 times square root of 3. And then finally, the last terms, when I multiply these together, negative square root of 3 times negative square root of 3 is actually just equal to 3. I guess I could, well, anyways. So that's the numerator. And I'll simplify that here in a second. What about the denominator? Well, the same kind of thing is going to happen. We end up with 3 times 3, and the outside terms are going to be minus 3 times square root of 3. But here's where the trick comes in, because the inside terms are actually going to be positive. So this is plus 3 times square root of 3. And then finally, the last term, we've got square root of 3 times negative square root of 3. This is actually going to be just minus 3. Okay, so they look very similar, but they're not. So what I'll do now is I'm going to collect these in terms of the radicals in the top. We'll have minus 6 times square root of 3, and then the non-radicals, 9 plus 3. So the numerator reduces down to 9 plus. Let me 9 plus 3 minus 3 root 3 minus 3 root 3. I'll do this in a couple steps. So that's the numerator. Now in the denominator, notice that this term is equal and opposite to this term, and so they will equal 0. This is why this process of rationalizing the denominator works. It's why you have to have a different SIGN to make this work. But that's sort of why we did it in the first place. So those two terms will equal 0, and all we're left with is 9 minus 3. Okay, so further simplification gives us 12 minus 6 times square root of 3 all over 6. Notice that every term there has a factor of 6 in it, and so the net result is that I end up with 2 minus square root of 3. So just to clarify, tangent of 13 pi over 12 equals 2 minus square root of 3. Okay? I think I'm going to stop here, and I'm going to debate whether or not I want to do a bunch of examples. I think I'd probably rather do some things, a different class of problems, rather than exact values. I want to do some things, known exact values. So I'll come back for at least a 4th segment, and we'll be seeing you.